So our next speaker is Willian Natori from Unicamp. Willian, the floor is yours, and I'm going to let you know when you have 25 minutes, okay?
Okay, can you hear me? Yes. So, thanks for the invitation, and now I'm going to talk about the spin-orbital Kitaev model as a parent Hamiltonian for quantum spin liquids in Rydberg simulations. So this work was partially done while I was still in France at La Langevin, but most of it was already performed here in Brazil. And it was done in collaboration with Rodrigo Pereira, who is my PhD supervisor as well as two of his former students. First, Wesley Fontana, who is a postdoc now working in Taiwan, and Fabricio was his PhD student, who is now in Taiwan as well as a postdoc. The results were published in this PRB this year, so everything will be contained there. And as many things that we studied today, the main subject of the matter, quantum spin liquids, was first conceived by Philip Anderson 50 years ago, more than 50 years ago actually. And he conceived a state of matter, a magnetic state of matter that would not be understood in terms of spin arrangements, one spin at each side of the lattice, but instead it would be described in terms of singlet coverings of the lattice, and not only one single singlet covering, but a linear combination of all possible coverings. This is now known as the RVB state, the resonance valence bond, and it's the first quantum spin liquid that we have some theoretical proposal about it. Originally, Anderson's intention was to describe a possible phase in the so-called geometrically frustrated lattices, where there were some multi-insulators being synthesized in this geometry. Unfortunately, until now, we don't have a decisively a quantum spin liquid in such solid state platforms. However, that doesn't mean that looking for quantum spin liquids have not been important throughout these 50 years. It's what I call a productive hide and seek problem. It started with these geometrically frustrated multi-insulators, as I recalled, but then there was some idea that quantum spin liquids, doped quantum spin liquids, could give rise to high TC superconductivity, also an Anderson's idea. Sometimes it's such that quantum spin liquids would be mini universes, in the sense that you have fermionic excitations that interact with each other through gauge, through emergent gauge fields. And finally, nowadays, in some two-dimensional quantum spin liquids, they can host no 1 billion anyons that could be used as platforms for topological quantum computation. Now, there's 50 years of high-quality research in quantum spin liquids, and a newcomer to the field could just simply ask where to start studying quantum spin liquids. And the pedestrian approach to answer this question is just Google it, and looking at Google Trends. And as you can see, if we start looking at 2010 as our benchmark, there will be two distinctive peaks on the search of quantum spin liquids in Google Trends. The first one is in 2012, and is related to Herbert smithite, a Kagome lattice compound here, in which the copper atoms are supposed to interact with each other through a Heisenberg model, right? So you have a isotropic spin model with spin 1/2. This is considered a good candidate for a quantum spin liquid. The other peak is related with this 2016 experiment describing the alpha-ruthenium trichloride, which say candidate for a Kitaev spin liquid, in the sense that the interactions. Sorry, where is okay? In the sense that the dominant interactions of this model are of the Kitaev type, so Ising interactions in different quantization axes, one for each one of these three directions of the honeycomb lattice. So this Kitaev model is exactly solvable in this, and we know for sure its ground state is a Majorana quantum spin liquid. This one, there is good evidence for the Heisenberg term here. But you can see that there are two different kinds of spin liquids, two different kinds of lattices, two different types of interactions. And my claim here is that Rydberg simulations provide a bridge between these two types of quantum spin liquids in 2 dimensions. And this is thanks to this work here. This is the experimental paper in Science by this group in Harvard who are working with quantum simulations. The theory, the first theory and very good paper was provided by Ruben Verheysen and Ashwin Vishwanath. So this is an important paper for us, but we will focus on things that they did not calculate related with the classical limit of this model. As a quantum simulation procedure, we always start with some cold atoms, in this case rubidium. And the rubidium will be mostly on the ground state, but if you excite it with a 2-photon process, it can resonate to a given Rydberg state here, and there will be 2 detunings related with this 2-photon process. In general, you will say that each atom will be either on the ground state or in this Rydberg state R here. And to each one of these states, you will be associating a given Ising variable, 0 for the ground state or 1 for the Rydberg state. Of course, you can you will excite many of such Rydbergs around on the lattice, but they cannot be arranged randomly throughout each, because a given Rydberg state will interact very strongly with another one through dipole-dipole interactions. So there will be a repulsion between Rydberg states that will order then throughout this Ruby lattice. Okay. So no Rydberg state is supposed to be within this circle here, within this radius. And everything will be described in terms of Ising variables at first, okay? Now, the idea that was in this paper is that if you start placing these atoms on this Ruby lattice and keep the density of Rydberg states to 1/4, you can map these Ruby lattice configurations here, the Rydberg states on the Ruby lattice, through some covering, singlet covering on the Kagome lattice, which would implement some form of Kagome dimer liquid. And as you insert quantum fluctuations to this model, you will have some resonance between different dimer coverings, and this would lead to the RVB stage on the Kagome lattice. So that would be how you would simulate a RVB stage on a programmable quantum simulator. So, okay, just to set the parameters of the simulation, you will have a parameter U here, which will be just the blockage within the triangles of the Ruby lattice. You will have some repulsion between Rydberg states in nearest neighbor triangles, okay? And you will have some longitudinal field related with this detuning here that can favor or disfavor the occupation of a given atom, of a Rydberg state on a given atom here. Concerning the transverse fields, you can start with this rabbit term that will just it will be concerned with this resonance between empty states and occupied states, if you will talk in terms of Rydberg states. And also the possibility that a given Rydberg atom can hop around a given triangle, right? In each of these transverse fields here, you will see a modulus and a phase associated with it for a complete description of the possibilities that we have. So how it works to map from the Ruby to the Kagome lattice. This is simpler in the sense that the Kagome lattice is the medial lattice of the Ruby lattice. So if you will pick this Rydberg state here, you'll see that it's on the bond of the Kagome lattice, and this one will be directly mapped onto a dimer state here. Okay, so there is a 1-to-1 correspondence between Rydberg atoms and Kagome coverings. But as illustrated in this picture, we can also do some representation in terms of a classical spin ice, right? In which we associate each one of these dimer here with some spin configurations. So in this case, we will associate each dimer here with 2 arrows inside the triangle, and the empty triangle as 3 arrows out, okay? So this is a form of a spin ice here, a bit different from the ones we normally study, but a spin ice anyway. And these are representations of the possible dimer coverings on a single Star of David that we have on the Kagome lattice. Now, if we want to map this Ruby lattice representation, Ruby lattice simulation on the honeycomb lattice, this is also possible. For this, we need to consider that each side of the honeycomb lattice corresponds to a single triangle. So the up triangle says on the A sublattice and the down triangle on the B sublattice, okay? Each triangle will have 4 possible states in the given density. So it will either be fully unoccupied, or it will have 1 occupied state, okay? And there will be bond-dependent interactions of the Kitaev type. Now, although the model is fully classical at the without transverse fields, okay? So the mapping between Ruby, Kagome, and honeycomb lattice is illustrated here. You will see the first one row is for the Ruby lattice, and then the second row for the Kagome lattice. The third row for the honeycomb lattice, you pick the spin ice representation and see that the out arrows will correspond to minus signs, and the in arrows will correspond to plus signs, okay? This can be related, can be described in terms of eigenvalues, eigenvectors, right? Eigenstates of these 3 operators here, AX, AY, and AZ, in which each one of these minus and pluses here correspond to eigenvalues of one of these 3 different Ising operators. Now, it will be convenient to rewrite these A gamma Ising operators in terms of a different representation that I've worked a lot about, which for spin 3/2, you can actually describe these pseudo-spins and pseudo-orbitals. And the pseudo-spins are here in terms of these exponentials of the S alpha, in which S alpha are the canonical spin 3/2 operators, while the T's here correspond to pseudo-orbital operators, and Ty is a special type of octopolar operator. The algebra of these pseudo-spins and pseudo-orbitals, they really resemble those of the spins and of the canonical spins in terms of commutation relations and anti-commutation relations. One important point is that these sigma and t's, they commute with each other for any value of alpha, beta, I, or j, okay? Several works have been published on this respect. You can just check it if you want more details on it. But for this particular talk, the important point is that the A gamma will be exactly equal to the product of sigma gamma and T gamma, okay? And this is interesting that when we translate the Rubby lattice model into the spin lattice on the honeycomb lattice model, the result term will be this spin 3/2 Kitaev model, which are called the spin orbital Kitaev model because the A gamma is a combination of spin and orbital degrees of freedom. The J here is related with the is equal V/4, which is a parameter of the quantum simulation, and the HL here is a longitudinal field, so it's still a classical term that's equal to V minus delta over 4, a combination of this V and G tuning. In the remainder of the talk, we will consider HL equals 0, for which this model, the spin orbital Kitaev model, is exactly solvable. Okay. So first we can rewrite those dimer coverings on the Kagome lattice into placket ground states on the honeycomb lattice. And one interesting feature of it is that all loops will that minimize all the energy here of each bond will satisfy WAP equal +1, where WAP is this product among these A gamma operators. For those who are familiar with Kitaev physics, this is the analog of these operators that commute with the Kitaev model and ensures its integrability. And so what I find here is a classical analog of Lieb's theorem for this spin orbital Kitaev model. Now, one interesting thing is that we can work up from this point to give the exact solution of the spin orbital Kitaev model. So we just pick one reference ground state here and verify that the spin orbital Kitaev model above will still commute with the placket operators characteristic of the spin 1/2 Kitaev model. And if we apply this operator on the reference ground state, we still have a ground state. So this is a way to generate a number of ground states, and in fact, there could be something of the order of 2 to the power n ground states, in which n is the number of plackets. In fact, it will be 2 over n minus 1. This minus 1 factor here is just related with the fact that if we have a product of all these WP sigma operators, we have the identity. So they are not totally independent from each other. Another form of symmetry that we have is our non-local symmetries. So if we apply a sigma z operator here on a whole xy chain, then it will also be symmetry of the spin orbital Kitaev model, and we'll have can construct another ground state by applying such a string operator on any reference ground state. Well, since there are two independent non-contractible loops, and since a single string cannot be given by a product of these WP operators, then there will be a factor of 4 degeneracy associated with these with these non-local symmetries, and we will cover something like 2 over n plus 1 degeneracy, which is exactly the number of dimer coverings on the Kagome lattice, which recovers this idea of the dimer spin liquid on the Kagome lattice that should be associated with this model as well. So far, I just talked about ground state properties, but we also have we can also find properties for the excited states. And in this case, we will always find that the excitations are created in pairs. So we will always have pairs of, say, WP A is equal -1 states on the lattice, or pairs of broken bonds, right? Yeah, unsatisfied bonds in energy. So the energy of the excited states should always come from these two any unsatisfied bonds, and we have an energy for each. And we can also calculate the degeneracy of such levels. There will always be a 2 over n plus 1 a term associated with symmetries times the arrangements of these 2n broken bonds on 3n bonds of the lattice. Summing over all these degeneracy levels, we recover the total Hilbert space. So we know that everything follows. We can reconstruct the entire Hilbert space by doing such computations. And now we can try to compute the partition function using this formula for the degeneracy times a Boltzmann factor. And we can have an analytical expression for the partition function that's just some polynomial term. So this means that we can calculate the entropy and the specific heat exactly. And in particular, we can calculate the entropy, the 0-point entropy here associated with this exponential ground state degeneracy, which on the thermodynamic limit will be lead to a 1/2 over 1/2 times ln of 2 as the entropy per site on for this spin ice state, right? For those who want to check with some numerics, there was this independent work done at the University of Tokyo that was published this year as well for the same model, and they retrieved the same results, but they need to use Monte Carlo instead of exact computations. So it works, okay? Other thing that we could compute exactly is the static structure factor. In this case, we used a result that was known for the Kagome dimer liquid, that there are ultra-short correlations between the dimers. And in the case of the spin orbital representation we're using, this is translated by ultra-short correlations between AI and alpha and AJ beta, much like the exact results of the spin 1/2 Kitaev model. So in this case, we can use this result to compute the static structure factor exactly and find this expression here, leading to this very interesting static structure factor. You can see that there are no pinch points as you would see in these spin ice liquids, right? So these spin ice states, but we have a Z2 spin ice, not a U1 spin ice, so do not expect such pinch points anyway. But there are no Bragg peaks as it is expected for the absence of order. That paper I was talking before for Monte Carlo simulations, they did the same. They computed the same structure factor and found the same result. So, concerning quantum fluctuations, we just order the bases this way and find that the Rabi terms they will have this matrix form, which can be rewritten in terms of pseudo-spins and pseudo-orbitals, and they will have correspond to this combination of spin and orbital operators. We can do the same trick for hoppings, giving another combination of spin and orbital operators. Okay. Such quantum fluctuations were already considered in this Ferris and Vishwanath paper, and all fluctuations can be considered transfer fields. Okay, for the spin orbital Kitaev model, but in perturbatively, all of them would induce resonances on these Kagome coverings, which means that they would lead to some form of RVB stage. But most interestingly, there are some special cases in which, say, you have Rabi and hopping terms with the same absolute value, and and they are both real and greater than 0. In this case, we can take a limit where these transverse fields are very large, and this will induce a spin-1 quadrupolar Kitaev model. The spin 3/2 version was also studied by Vanuildo, Eduardo, and Rodrigo, so it's a well-known model, but the spin 1, there is still no analytical study on it. If we take imaginary Rabi and hopping terms, again with the same absolute value, then in the limit where these transverse fields are very strong, you will induce the spin 1/2 Kitaev model with 1-1-1 field. And interestingly, this year, the phase diagram of this model was uncovered with IPEPs leading to a transition from a chirospin liquid to a Majorana metal phase. So also a very interesting phase to be studied. And the key message is that Rydberg simulations on the Rabi lattice, they are bridging these Kagome and Kitaev spin liquids. These are the conclusions, okay? So some perspectives are, well, we could try to do quantum Monte Carlo simulations on the full honeycomb lattice model, right? This was possible for the full Rabi lattice model, and in a publication done this year, which also found features of the spin ice system I just described for a large range of parameters of the simulation. So maybe we can give further insight by just getting this spin orbital Kitaev model. How much control do we have over the parameters? In particular, how much control we have over these hopping terms? Can we control the absolute value in phases by saying apply some Fouquet engineering? I don't know. Out of equilibrium physics of both the classical and quantum model, because of course the quantum simulations are being performed in some non-equilibrium regime. How can we provide non-destructive probes to analyze the correlation, the dynamical correlations of such models? And finally, one thing that's related with the first talk of this session, which is on the possibility of describing other kinds of spin ice systems using variations of the spin orbital Kitaev model. So recently there were studies on the Heisenberg model on the centered pyrochlore lattice by Rydberg, Ludwig, and Lode Pollitt. And in contrast to the usual spin ice states, they're characterized by three in and one out states on each tetrahedron, or one in and three out. And apparently these states could be described by a spin 7.5 gamma matrix model on this pyrochlore lattice with similar characteristics of the spin-orbital Kitaev model. So with that, that's all. Thank you.
Thank you, Willian, for the very nice talk. Do we have questions?
Mhm.
Oh, sorry.
Thank you. Regarding the choice of bases for your quantum fluctuations, are we expected to have some anomaly phase or accumulation of geometric phase around the closed loop?
That's a good question. I didn't think about this problem actually. Maybe, but yeah, I don't know. I mean, that's a good point. Maybe we could talk a bit more about it. But
More questions?
Yeah, just to understand, so the number of conserved quantities that you have per unit cell are 2 in this case?
the number of conserved quantities, let's see. Well, there will be one conserved quantity per package, right?
Yeah.
And there will be two independent non-local string symmetry, right? So there will be two independent strings, say one in this XY direction, or XY chains, and other in the YZ chain, say, for example. And one cannot be contracted on the other, so that's the point.
There are only 2 in the entire torus, or is it one for each line? That is
One for each line, but
Okay.
let's see.
Okay.
One for each line, but the key point is, do we have an even or odd number of loops that were applied on the reference ground stage? If it's even, then we can reconstruct these string operators by combinations of these WP sigma operators. But if it's odd, it's not the case. You cannot do this. So then these non-contractible loops become a symmetry of its own. Okay.
Is there any idea of, because the examples that you showed are of spin liquids when you add perturbations are similar to the usual Kitaev sort of spin 1/2 model. But are there any ideas of how to get new kinds of spin liquids when you add other perturbations that are not similar?
Well, okay. The examples were considering the Kitaev spin liquids because they are simple, right? But on a first approximation, each one of these would generate some gauge flux excitations, okay? So you could use some formalism such as augmented partum, mean field theory, or variational approach to introduce some of these states with Z2 gauge fluxes inserted on the Kitaev model and start doing other analytical theories on it. But yeah, it would be a bit more of work. You will have to adapt the technology for a spin 1/2 Kitaev model, but it's possible. Yeah. But it.
More questions?
Thanks, William, for this really nice talk. So you, to get your analytic solution, you put your field to 0, right?
Yeah.
So what would be the key effect of the field? How would it change? I mean, would this still be possible to get this some sort of analytical solution in the presence of the field?
Well, by the end of our work, we showed that perturbatively, these results will conserve for small HL, okay, small longitudinal fields. For large HL, we know that depending on the sign of HL, you will project your Hamiltonian to a spin 1 sector. But analytical results for these large fields, I don't think we have it right now. Okay, so we would need some form of Monte Carlo simulation. That's why I'm also interested on these Japanese papers. Okay.
Thank you.
There is time for one more question.
Not that I know. I mean, for the Kitaev honeycomb model, I don't think so. Yeah, it's a complicated problem. From the last time I saw this, there were two different approaches, one using DMRG and one using tensor networks, and they gave different results. And also, yeah, it seems that the Kitaev model has some form of even-odd effect. Depending on the number of states at each site, you will have a different physics. So, yeah, it's not very clear what spin 1 Kitaev model would give. Okay.
More questions? If not, let's thank you, Willian, again.
Mhm.
Thank you.